So we were talking about what happens when a wave encounters a boundary between one medium and another medium. Okay? The medium in which a wave travels determines the speed of the wave. So if a wave goes from one medium to another, its speed will change. What else will change? Its wavelength. What won't change? Frequency. I think that's 32 times. We've gone over that now. Okay? Frequency of a wave doesn't change. So in this case here, okay, where we have a pulse traveling in a more dense medium, okay, and going into a less dense medium, right, we're going to have some things happen. First off, some of the wave energy, not very much, but some of it is going to reflect off of the boundary, and that's what we see here. This is a reflected pulse. So when the wave here encountered that boundary, not all of the wave energy got into the new medium. Some of it reflected off the boundary. That always occurs. Okay? Whenever there is a boundary between one medium and another, some of the wave energy will be reflected off the boundary. Okay? A lot of the wave energy got into the new medium. And we can see that some of the properties of this pulse are different than the original pulse. This pulse is longer. If this pulse is longer, then it's also traveling faster. All right, so when we go from a more dense medium to a less dense medium, speed and wavelength increase, and our reflected pulse is upright. That means it is the same as the incident pulse. Okay, that's the pulse that came in. Everybody with me there? All right. When you have the opposite situation going on, so I have this pulse traveling in a less dense medium, and it's going to travel into a more dense medium. Is that going to make it more difficult for that wave to travel? Yes. That means more of that wave energy is going to reflect. Less of it is going to be transmitted through into the next medium. So a little while later, after the wave has encountered the boundary, we see a fairly large inverted reflected pulse. Okay? Anytime you get a reflected pulse that is inverted, it means the medium it went into is more dense or slower, okay, than the medium it came from. Okay? That's what an inverted pulse always means. An upright pulse always means that it's going into a less dense medium. Now, we can also tell that by looking at the transmitted pulse. Not only is it smaller, it's also shorter, okay? Which means that it had to do what? Slow down. The back of the wave caught up to the front of the wave, okay, making the wave shorter. Right? So the wave is shorter and slower, and the reflected pulse is inverted. Right? Everybody follow me there. Okay? That's just something you're going to have to memorize. Now I'm going to show you what that looks like here with a couple of slinkies in just a second. Terminology-wise, okay? Incident pulse, incident always means the one coming in. Okay? Transmitted always means the one going out. Reflected also means the one coming back. Okay? So those are kind of terminology there. Now, sometimes you will see, instead of the word upright for this pulse, you will sometimes see the word that it is an erect pulse. I don't use that because it gets exactly that reaction from immature people like you. So, okay, I always use upright. But once in a while you may actually see that an erect pulse is reflected off of the boundary. Okay? I know your heads are in the gutter. They're there with the rest of your body. But, you know, yeah. Okay. All right. So just keep that in mind. It's just terminology. Okay? And if it's an inverted pulse, that means that it's opposite. So if the pulse coming in was a crest, the pulse coming out is a trough. It's inverted. Okay? Everyone all right with that terminology? Okay, so that's just something, guys, that we're going to have to memorize, okay, so that when on a test you can, when you get pictures like this, you'll be able to tell me. Because on a test, what I would probably do is say something like this. Right? I would say, in this situation here, okay, this is kind of the setup. So here's medium 1, here's medium 2, here's medium 3, and then a little while later, okay, a little while later, I see this situation. Okay, so this pulse is traveling that way. This is a reflected pulse going this way. Okay, I've got an Okay, I would have this situation a little while later, and then I might ask you something like, what are the relative densities of the three media? Okay, well, if this pulse here is coming back inverted, then this medium, the second medium, is it more or less dense than the first? More. Okay, I also have a reflected pulse coming back in the second medium, but it's upright. Well, that means then that medium 3 is more or less dense than 2? Less. Okay? That sort of makes sense? Okay, that's the kind of thing you'd be asked to do with this type of information. Okay, when a pulse hits something that is more dense, it reflects back inverted. When it hits something less dense, it reflects back upright. Most of it goes through. Okay. All right, so for reflection, okay, if wave energy reflects from a more dense medium, okay, then it will reflect back inverted. So like a water wave coming in hits a cliff, it reflects back inverted. Okay, reflection from a less dense medium, okay, results in an upright or right side up wave, okay, like a sound going from water to air, or something along those lines. Okay, the thing to remember about reflection is that whatever angle the wave comes in at, that's the angle it's going to come off at. Okay, so if I have a wave comes in at 45 degrees when it hits a reflecting surface, it's going to bounce off that reflecting surface at 45 degrees. It's called the law of reflection. The angle of incidence, that's the angle it comes in at, is equal to the angle of reflection, always. Okay, and you've probably taken advantage of this at some time if you've ever tried to reflect the sun off of your watch face into somebody's eyes. Okay. You've probably all done that at some point. Okay? If you're trying to reflect something off, you have to get the angles right. Okay? Because the angle of incidence always equals the angle of reflection. And that can come in useful in certain situations, like in pool. Okay? How many people play pool? Okay. Anybody able to consistently hit a bank shot?
Yes.
Okay. After today, all of you will be able to consistently hit a bank shot. Okay? Bank shots are way easier than people make them out to be, right? Because it's simple physics. So if I have a cue ball here, and I want to hit this ball over here, and I can't do that directly because the 8 ball is in between, okay? Then I have to hit it off the bumper, and then this way. The key to doing that is understanding the law of reflection. Whatever angle this comes in at is the angle it will come off at. Everybody okay with that? Okay, so here's what you have to do. You can't just estimate, because that's what everybody thinks they have to do, and then they miss the shot. There's actually a scientific way to make sure you always hit it right. You have to treat the bumper like a mirror. Have you ever noticed that if you stand 1 meter in front of a mirror, your reflection stands 1 meter behind it? You probably haven't noticed that, but it's true. And if you back up a step, what does your reflection do? Backs up a step. And they'll be the same distance behind the mirror that you are in front of it. Okay? So, what I do is I have my friend stand behind the bumper with a cue as far behind the bumper as the ball is in front of it. So, I take, sorry, that's a bad line to draw. The color we can see here. Okay, so what I do is I have my friend stand that far behind the bumper, and I aim at his cue. Because then, when the ball hits the bumper, as long as it's not spinning, it will bounce off at exactly the right angle to hit this ball. And it'll work every single time because it's physics and it's irrefutable. Now, if you're playing pool in a pool hall or a bar, people don't always like you to do that because they think it's dirty pool, okay? Especially if they catch on to what you're doing, okay? Because I know a friend of mine and I, but this is how we would always play pool, okay? One of us would stand back there like this and go, "Ah, nice shot, buddy," and people wouldn't really notice, but if they did notice, they'd get all cranky about it, and like, hey, it's a game. But sometimes they get upset, okay? But this is how you can pull that shot off basically anytime you want, okay? It'll always work. So next time you play pool, that's the trick, okay? All right. Good, I got those videos I gotta show you. Okay.
Yeah.
And reflection is one of the ways we can change the direction that a wave travels. Okay? When you reflect a wave, you actually don't change anything about it. okay, other than the direction it's traveling. Reflection will not change the speed of the wave. It will not change the wavelength of the wave. It doesn't change the frequency of the wave, but it will change the direction the wave travels. Okay? So that's one of the behaviors of waves is reflection. Okay? All right. Transmission. If a wave goes through and into a new medium, then it is called the transmitted wave. Okay, so transmission means it goes past the boundary and into the new medium. Okay, transmitted wave is always going to be upright. So if I had a crest coming in, I'll have a crest going out. Okay, if I had a trough coming in, I'll have a trough going into the new medium. Okay, the reflected wave, that could be upright or inverted. Okay, but the transmitted wave is always the same as the incident wave. Okay, frequency remains the same, controlled by the source. Okay, velocity will change because the medium controls the velocity. Okay, the wavelength will change because velocity changed. Okay, amplitude also changes. You're going to lose some wave energy at a boundary. And amplitude is what represents the energy of a wave. So when you lose a little bit of energy, okay, you're likely to have a change in amplitude of the wave. You could also get a change in amplitude of the wave if the wave slows down, because then the front of the wave and the back of the wave get closer together, and it might make the wave a little bit taller. Right? Okay, now rays are things that we draw just to represent waves. Not going to be really important in Physics 20, but you'll use them a lot when you draw ray diagrams in Physics 30. Okay, so a ray is just an arrow that represents a series of waves traveling through, so you don't have to draw all the waves. Okay, a normal line is the line from which all angles are measured. So when we were doing this this question here, okay, or this situation here, the normal line would have been right here. Okay, the normal is always drawn perpendicular to the boundary, and then we always measure the angles from the normal. Right? So this is the angle of incidence, and this is the angle of reflection, and those angles are always equal. Okay. Everybody with me there? Okay. So the normal line is just a line that we draw. It's an imaginary line that we can measure the angles from. Okay, and then this is the law of reflection. The angle of incidence equals the angle of reflection. Okay, that's always the case anytime there is a reflected ray, okay, a reflected wave. All right, when we're talking about refraction, okay, refraction happens only with two-dimensional waves, okay, not with waves on a string, okay, because they only come in one direction, okay. But if I have waves coming in at an angle, and they go into a new medium, their direction will change because part of the wave gets slowed down before the rest of the wave, or part of the wave speeds up before the rest of the wave. So what we have in this diagram here, okay, is these incident waves, and they're coming in. If I draw a ray that represents those waves, it goes like that. Okay, this would be the normal. Everyone with me on that? Yes? Okay, now when these waves that are out here in a medium that is fast, and we're going into a medium that is slow, by the way, how do I know this one's the slow one?
It's closer together.
The waves are closer together here. Okay, if I look really closely, I can see that the wavelength out here in the white part is longer than the wave in the blue part or green part. Okay, so these waves are coming in, and you can see right here that as a wave encounters the new medium, it gets bent. Okay? The reason it gets bent is because this part. Okay, so you can see that with this wave here, okay, that the wave was bent, right? So this part of the wave slowed down, but this part of the wave out here was still traveling at the faster speed. So this part of the wave here falls behind it. And that's what causes the wave to appear to bend, because part of the wave is traveling slower than the other part. Okay? Now, what that means is that's also going to change the direction in which the wave travels. Okay? So if, let's say, I'm kind of walking along and I have my arm out, I'm walking in a straight line and my arm hits the desk, what do I start to do? Well, maybe, probably not. Okay, but as soon as I start, if my hand catches there, look what happens to me. I turn. Okay, Now, this part of me, okay, the outside part of me is still traveling at the same speed I was traveling before, but this part of me slowed right down, and because I'm connected, okay, it pulls me and causes me to turn. Okay? The same thing is happening to these waves. Okay? Part of them is slowing down, falling behind, and pulling the rest of the wave along with it, causing it to change direction. So this was the direction of our incident waves, okay? But this is the direction of our refracted waves. Okay? So it bends towards the normal. Okay? This refracted one is closer to that normal line than the incident one is. Okay? The opposite is true if the waves go the other way. Okay? If the waves go the other way, so that now they're going from slow to fast, okay, as the wave starts to get out, the part that gets out first runs away from the rest of the wave and actually bends away from the normal. Okay? So here's our incident waves, okay, and here's our outgoing waves. Okay? Bends away from the normal, okay, and speeds up. All right, everybody okay with how that works? I've got a couple of videos on refraction here. So, refraction means, okay, that we've got this with these waves that are entering a medium at an angle, okay, and when they enter at an angle, their direction changes because their speed changes, their wavelength changes because their speed changes. Okay, remember that the frequency will remain the same. All right, and that's kind of what we were showing here. I was talking about the spearfishing example. Okay, so my eyes would perceive the fish to be in this area here, when in actuality the fish is here, but the waves that come from him, or the light that comes from that fish, they bend away from the normal, okay, and make them appear to be somewhere else. Okay, and then obviously if you got light coming into a slower medium like water, then it bends this way and slows down. All right. Okay, and again, we can see that here. If we put like a sheet of triangular glass inside of a ripple tank, okay, we can see that the waves slow down. Okay, they get shorter in the area where they travel slower. Okay, that can also cause a change in direction of the waves. Okay, out here in the deep water, the waves are a certain distance apart. When they get to the shallow area here, they're slowed down and turned, and that pulls them in. Okay, changes their direction. Okay, that way. All right, last behavior of waves, and I'm not sure if I remembered to put this one in your notes, because I think something told me I missed it in your notes. If it's not, you'll need to write it down. Okay, diffraction is the last behavior of waves that we're going to talk about. Okay, diffraction happens when waves have to either go around an object or through a narrow opening. Okay, we all know that one of the things we kind of just instinctively do if we want to, kind of increase the ability of our voice to carry. Okay, one of the first things we do is obviously increase our volume, and then instinctively we do this. Why do we put our hands around our mouth? It doesn't echo it. What does it do to the waves? It focuses them. Okay? It makes, instead of them spreading out directly from my mouth, it focuses them through this narrow tube, okay, which makes them do this, okay, and it keeps them in that narrow range, okay, and helps then for that energy to remain kind of there, okay, direct my waves a little better, okay. That's diffraction through a narrow opening. Now, diffraction through a narrow opening can do a number of things, okay. The first thing it does is actually bend the waves. Okay, it does that because the edges of the waves catch on the opening. Okay, so they catch on the opening and they're slowed down while the middle of the wave goes through pretty much unmolested. Okay, and so what ends up happening is the wave curves. Okay, that sort of makes sense, everybody? Okay, if the wave curves, okay, then obviously it's changing shape. Now, that means it spreads out a lot differently. If I only had this narrow opening and waves didn't diffract, how much of the wave would get through? Just this much of it. Right? If waves didn't diffract and they hit a narrow opening like that, only that much of the wave would get through. That means if I was over here and this was sound, would I hear it? No. Okay? But if people are out in the hallway and the door is open, I can hear them anywhere in the room, can't I? Okay, that's because when their sound waves come through the narrow opening of the door, they do this. They diffract. They become rounded. okay, and they spread out through the entire room. Now, believe it or not, it is this behavior that proved light was a wave, because for a very long time, most scientists, Newton included, believed that light was a particle. Okay? Light couldn't be a wave because light didn't do this. Think about it. If light diffracted, okay, and that means it could go around an obstacle, okay, like these waves have, okay, or through a narrow opening, what would you not have? You wouldn't have a shadow. Okay, if light's a wave, it would just diffract around you, and you wouldn't have a shadow. Okay, if I had the lights off in here and the door open, there's only a thin beam of light coming through the door. Okay, well then light can't be a wave, because if light was a wave, it would diffract, and the whole room would get lit up by just having the door open. So how can we prove that light actually does this, or why does it look like light doesn't do this? Because this is the evidence that people had. They said light is not a wave because of these very easy to observe things. Okay? If light was a wave, you wouldn't have a shadow. But I have a shadow and light's a wave. Okay? The reason is this. Light has the two properties of a wave that make diffraction very, very difficult. It's very, very fast. And it's very, very short. Okay? The wavelength of light is incredibly short. It's measured in nanometers. Okay? Its speed is incredibly high, 3.0 times 10 to the 8 meters per second. The faster a wave moves, the less it will diffract. Okay? Because the less it is in contact with the thing it has to diffract around or the opening it has to diffract through. Okay? If a wave is long and slow, it will be in contact with this opening for a long time, increasing the amount of diffraction that can occur. If it's an incredibly fast, incredibly short wave, it's hardly in contact with that opening at all. It just goes right through and hardly diffracts at all. Okay? But light does diffract. And it was proven by a guy named Thomas Youngs. He did an experiment that nearly got him laughed out of every place he went, until he showed everybody it worked. Okay? He said, light's going to diffract just like a wave because it's going to behave like sound does. And he set up an example that's like the two-speaker question we did the other day. Okay? Where we tried to determine whether a person standing here would hear a loud or quiet sound. Remember that? Okay, and that was based on the waves meeting crest to crest and trough to trough here. Okay? So what he said is, I'm going to prove that light's a wave by doing an experiment like this. I'm going to have a light source back here, and in front of that light source, I'm going to have an extremely narrow opening. And then a little ways away from this narrow opening, I'm going to have a barrier that has two equally spaced, very small openings. And what I'm going to get is, on a screen out here, I'm going to get patterns of light and dark, light and dark, light and dark. And everyone looked at this setup and went, are you nuts? Because what did they think light was going to do? Go through the first opening, hit this barrier, and then end of experiment. You are an idiot. Okay, everybody knows what light's going to do when you do this experiment. Okay, except he had figured out that light not only traveled very fast, but had an incredibly small wavelength. So he spaced these two blocks essentially, so that when the light came through this opening and diffracted, which is what it did, it actually struck these two openings, making each one act like a separate source of waves, just like the two speakers. Okay, so we had waves coming from this one, and he had waves coming from this one over here. Okay, now if he puts the screen right here, okay, he gets patterns of light and darkness. Anywhere where two waves overlap, which I didn't do a good job of drawing, okay, anywhere where two waves overlap, like right here, would be a bright spot. Okay, anywhere where there's just a single wave, like right here, there would be a dark spot. And then where they overlap, a light spot, and so on and so on and so on. Okay, and we kind of follow his experiment there. Okay, because he got light to actually get through that apparatus, and show the striping on the screen, he proved light was a wave. Okay? It was a groundbreaking experiment. Right? It proved unequivocally that light diffracts and is as a result of it. Right? But up until then, everyone thought light was a particle and that this experiment was stupid. All right. So, diffraction very simply is the bending of waves around an object or through a narrow opening, resulting in a change in shape of the wave. One other thing you're going to want to write here, okay? Shorter / faster waves diffract less. Okay? And then vice versa. Longer, slower waves diffract more. Questions on diffraction? Okay. So probably the way I'm going to test this would be I'd show you different pictures of waves doing things, and you'd have to identify whether it's reflection, refraction, or diffraction, okay, or maybe interference or something like that. All right, so I'm going to have you guys working on this, these questions here. They're on the end of page 4 and the start of page 5. Okay, they're asking you about waves at a boundary. There's some interference questions, asking you to draw some stuff in terms of behavior of waves, because that's exactly what I'm going to ask you to do on your test. Okay, so I want you guys to work on those, and I want to be able to go through those in about, let's say, 15 minutes. Okay, there's no calculations here. This really shouldn't take you all that long. You're basically just drawing some pictures. Okay, so I'm going to give you about 15 minutes to work on these. Okay, like I say, bottom of page 4, start of page 5, and you're going to do up to number 11. Okay, there's actually no calculations until you get to question number 11. That's the first one that's got calculations, and it's a 2-speaker question like we did the other day. Okay, all the other ones are just either drawing a picture or identifying what type of interference is occurring, constructive or destructive, okay, that kind of thing. Right? So let's get to work on those, and in about 15 minutes we'll go through. Okay, let's have a look at a few of these here, guys, before we run out of time. So everybody looking up here, please. So question number 1 is asking, draw a sketch of a trough approaching a fixed end. So in other words, I've got like a slinky on the floor, but it's attached to the wall. All right. When I make the wave, it's going to hit the wall, and it's going to what? It's going to come back. Is the wall more dense or less dense than the slinky?
More dense.
It's more dense. Okay. So I'm going to have, this is my before picture. Okay. Pulse is traveling towards the fixed end. A little while later, I'm going to have a pulse going back. That's inverted from my original pulse. Right? Anytime you hit a fixed end, it reflects back inverted. All right. For question number 2, draw waves before, during, and after complete destructive interference. If I'm going to get complete destructive interference, my pulses have to be opposite. Okay, so I've got an upward pulse traveling to the right and a downward pulse traveling to the left. Okay, there's my during picture. Right, they completely cancel each other. My after picture needs to show the 2 waves traveling on, completely unaffected by the fact that they pass through each other. Okay? They don't bounce off of each other or anything like that. Okay? We have to indicate that they continue doing what they were doing before. Questions on that one? Okay. Now, for this one here, okay, it's asking us, this is the before picture, and this is the after picture. All right, so I've got an upward pulse approaching a boundary, and then a little while later, I have a reflected pulse that is inverted, and I have a transmitted pulse that's upright, much smaller, much shorter. Okay, now there's 2 things there, 2 pieces of evidence that tell me the correct answer. The correct answer is that the second medium is more or less dense. More dense, and the 2 things that tell me that are the reflected wave is inverted, and the transmitted wave is shorter. Okay? Not just smaller, but also shorter. Okay? All right. So in this situation, I've got this upward pulse traveling in the slinky, and it's going to a light thread. Which is more dense, the spring or the thread? The spring is more dense. All right. So when this pulse gets to A, some of it will be transmitted, and some of it will be reflected. That's all you have to say about what happens at A. Some of it will be reflected, some of it will be transmitted. Okay, is the reflected pulse upright or inverted? Okay, well, if I'm going into a less dense medium, my reflection will be upright. Okay, what happens when the transmitted pulse reaches B? When it gets to B, it will reflect off. Will that reflection be upright or inverted? Inverted. Okay. All right, a long spring runs across the floor of a room and out the door. A pulse is sent along the spring, and a few seconds later, an inverted pulse returns. Was the spring attached to a wall or lying loose on the floor? Attached to a wall. If it was lying loose on the floor, what would happen? Actually, you'd have an upright pulse come back, because it would travel from the spring and into the air, which is less dense than the spring. You'd actually get a small upright pulse coming back. Okay. Number 6, if I want to make wavelengths longer, then I need to use a higher or lower frequency? Lower. Okay, I want to make waves shorter, then I use a higher frequency. Make waves longer, I use a shorter frequency. Okay? Okay, for number 7, I've got a pulse on this rope, which is a light rope, heading to this heavier rope. All right? When the pulse gets to A, some of it will be reflected, some of it will be transmitted. That's what we have to remember. At any boundary, that's what happens. Okay? Now, is the reflected pulse going to be upright or inverted? Inverted. It'll be inverted. Okay? This is a heavier, more dense material, so the reflected pulse will be inverted. When the transmitted pulse gets to B, it will reflect inverted. Property waves never changes. Frequency. All right. In this diagram, draw the waveform that would result from the two waves interfering with each other. Okay, what kind of interference is this going to be? Constructive. These waves are in phase with each other. Okay, so my resulting wave at the highest point is going to have an amplitude of 6, at the lowest point -6. So basically I just need to make a wave that looks like this. Okay, is that exactly what I'm going to ask you to do on your unit exam? Yep. Okay, so be ready for a question like that. Okay, in number 10, identify what kind of interference is occurring at these locations. So at G, what kind of interference is occurring here at G? It's constructive. They're both up. They may not be in phase with each other all that well, but they're both up. Okay, at I, destructive. Okay, one wave is up, the other is down. Okay, at K, destructive, one is up, the other is down. Okay, and at O, destructive, one is up, the other is down. Okay, now for question 11, that's your 2-speaker question. Okay, so we've got one speaker here, we've got one speaker here. We know that they are 6.42 meters apart. Okay, and that a person is standing 6.8 meters directly in front of one of them. I need to figure out whether they hear a loud or quiet sound based on the frequency of the sound and the speed of the sound. All right, what can I calculate right now with those two bits of information? The wavelength. Okay, so I'm going to calculate wavelength by going V over F. 400 divided by 340 gives me what? 1.2? 0.85? Oh, sorry, I got this backwards. Sorry. 340 over 400. Okay, so our wavelength is 0.85 meters. Listen, please. Okay, now what I need to do is figure out how many waves are in the 6.8 meters and how many waves are in this side that I still don't know. So I need to calculate the side I don't know, okay, and then do the same thing we did before. You're going to have a quiz tomorrow. It's Thursday, so be ready for that.